Okay, perfect. All right, now that I've officially started recording, I didn't get too far into the lesson today, which is good. So we are talking in 4.6 just about this new word called sinusoid. And basically what that means is that it follows the same pattern as a sine curve of a graph. So we're going to do two examples of graphs and see how, like what the difference between them is. So that's why I've got my graphing calculator up here. I'll make it a little bit bigger and I'll make us either smaller or go away. So we're going to graph y equals sine of x squared. So the x isn't being squared, the entire function is being squared. So I'm going to go to y equals, and I'm going to do parentheses, and then I'm going to do my sine of x, and I'm going to end all those parentheses, and then I'm going to square that. So we're going to square all of that. Now, I do want to tell you right now to make sure that your mode is in radians, not degrees. So I'm going to graph it since I'm in degrees really quick so you can see how you know that you're wrong. If I graph it and I just get this straight line, we know it's a sine graph, so it shouldn't just be a straight line. Something's got to be off. So the minute I see that, I'm going to go to mode and know that I need to be in radians. We're not doing a ton of graphing, sines, etc. on the calculator, but if you ever do, put it in radians. That's how your calculator reads it. So we're going to go graph that now. And so I'm like very far zoomed out, but as you can see, where am I? Okay, there we go. As you can see, I've got this little sine curve now. So I've got a sine curve going on. It looks like, as I zoom in a little bit, not that much, I guess. If I were to follow along with my graph, like normally I just press trace on the calculator, but I can just physically do it with my finger right here because of the calculator I'm using. It hits the axis, it hits the like x-axis again around 3.1 something. And if you remember, pi is the same thing as 3.14. So it hits 0 at 0, 0, and then it comes up and then it comes back down at pi. So we're going to graph this in terms of pi. So I'm zoomed in on my graph over here. I'm going to put a mark for 2 pi, and I'm going to put a mark for pi. And I'm going to put a like 0 at 0 and at pi and at 2 pi. So it actually hits the axis at those points. It's kind of like an upside down cosine curve technically, like it starts low and its highest point is in the middle. The only thing is it doesn't go from -1 to +1. It's like it got shoved up to just be between 0 and +1. So, and I could even zoom it in a little bit more and see that. There we go. That's kind of as zoomed in as I can make it. And so I'm going to go as high as 1 in between 0 and pi, and then also between pi and 2 pi. And that gives me kind of my sine-ish curve I've got going on here. It's as if I just kind of collapsed it down to be in half of the distance than what it normally is. And it doesn't, and it starts at 0, 0 again, but its highest point is 1, not anything above that. And then its lowest point is still 0. So I could also do it on the other side. Let's say this is my 2 pi, and this is my pi. I've got zeros again here on 2 pi and pi, and then I'm the highest in between them somewhere.
Why doesn't it go below 0?
Because of how the square works. So when we do like sine of something and then we square it, it makes it a positive number. It's a good question, Jared. And actually, we don't need to know that much about it. We'll do more with squares of sines later in the next couple units, but for this, it doesn't really matter. We're just kind of observing patterns of the graph. The next one is going to be different. So I'm going to tell you right now, it's not going to be this nice, pretty sine curve. So this one's a little bit different than we're used to seeing. But at the end of the day, if I zoom it out, we'd all say, oh, this looks like a sine curve. It just goes back and forth like we know sine curves do. The next graph I'm going to do is I'm going to erase that one, clear it out, and I'm going to do x squared plus 2 times sine of x. So that's the second equation we're going to do. X squared plus 2 sine of x. Now, when I graph this, whoa, that does not look like what we just had a minute ago. It looks kind of like this funny, like almost like a parabola, but like one side's kind of like lopsided out than the other side. It also goes a little bit lower than 0, 0. It's got like a weird dip. So it's got like kind of this funny parabola shape as we go through it. So I'm just going to mimic this as close as I can. It doesn't need to be perfect on your paper. So I'm just going to, I know I go through 0, 0. And then I kind of dip a little bit lower than that here. And I do a little curve and then I come back up. I know my drawing's not great, but we can all agree this is not what sine looks like. This is not a wave. It's not a curve. It's nothing. This doesn't look like sine, even though I do have sine in my equation. The reason it doesn't look like sine is when we do x squared plus the sine, that alters it, that it doesn't keep its wave pattern. And that ties into the word I'm going to teach you today in this section. It's called sinusoid. So you read it like sin, like in the Catholic Church, we sin, you, soid. So it's kind of a weird word, but sinusoid is how you say that. And a sinusoid is basically like a type or a shape of a graph, a shape or a type of graph that mimics the sine wave. So it does the little sine wave. That's all this means. Sinusoid means waves like sine. It's the shape or the type of graph like sine. Now, to keep us from graphing all of these and saying yes or no, does this work? We are going to simply just look at one quality of this graph. These equations, these functions will be sinusoid if they have the same period. So if like the horizontal timing is the same, then it will be sinusoid. So what we're going to do is look at all of these, and it's something of one function plus another function. If they have the same period, we're going to say, yes, it's a sinusoid. If they do not, we're just going to say no and move on. If you go back and look at this, x squared, we've never talked about like a period for x squared. Like it's just a parabola. It's just that shape. So that's why this doesn't look like a sine wave function, is because x squared and then 2 sine x aren't the same like period or horizontal distance or whatever you want to call it. So this one's not a sinusoid. And now instead of graphing the following, we're just going to decide whether their periods are the same or not. So I don't need my calculator anymore. I'm going to get rid of him. And we're just going to go one at a time through these and decide sinusoid or no. So the first one, I've got sine of x and then 3 cosine x. I don't care about the plus. I don't care about the minus. And I truly don't care about the number in front. The only thing that affects the period or the horizontal like stretch and shrink of a graph is if there's a number in front of my x. So sine of x, there's no number there. 3 cosine of x, there's no number in front of my x. So those have the normal periods of a graph. So I've got 2 pi and I've got 2 pi. Those are the same. That's it. We say yes. That's all we're doing. We're going to find the period. We're going to move on. The next one, I've got 2 sine of x and then tangent of x. 2 sine of x is 2 pi because there's no number in front of the x. Tangent of x, though, we remember from before, the period there is pi. These are not the same, so we're going to say no here. Any questions so far?
Wait, how? I don't understand why. So if they're the same, that's all. Like if they're the same, then it is a sense or whatever it's called. But if they're like, it doesn't matter if it's plus or minus or anything.
Nope. All that matters is the periods. So if it's the exact same period, so the first two are both 2 pi, then yes, that's a sinusoid. The next one, they were not the same, so it is a no. That's all we're doing. I don't care what they look like. I don't even care. The only thing I care about with the function is what is its period. So tan is not the same period as sine, but if that was like cosine, then that would work. The amplitudes out front don't affect anything, just the periods. So let's do a couple more. The next one is sine of 2x and then 3 cosine 5x. Now here I do have to double check some math because I've got 5 and I've got 2. Remember, to determine the period, we do 2 pi divided by b. So in this case, it's going to be 2 pi divided by 2. Well, that's the same thing as pi. Okay, so that's what we want to match. We want to match pi. The other one's going to be 2 pi divided by 5. And I can't simplify that, and it's also not equal to pi. So since these two numbers are not the same, then we say no. Sure, we'll just do it in the highlight. Okay. The next one says pi sine of 2x, and then pi sine of 3x. So 2x and 3x. Yes, they both have the same amplitude, but as I stated, the amplitude doesn't affect anything. And even though a pi amplitude would be funny, we could technically graph it. We could go up pi, we could go down pi, whatever. What we do care about is the period. So 2 pi divided by this case is 2. Well, we just did that a minute ago. We know that's pi. And then pi sine of 3x will be 2 pi over 3. Well, 2 pi over 3 is not pi. They're not the same, so we're going to say no again. Two more. Cosine 2 pi of x and 3 sine 2 pi of x. I've got 2 pi in front of both of them. And some people by this time, they're like, okay, I know if it's the same b, then the period should be the same. You can do that shortcut, but if you forget, I can still find the period. 2 pi divided by 2 pi means a period of 1. It's kind of weird, but whatever. It's okay. We did the rules. We followed the steps. Same thing over here, 2 pi divided by 2 pi. Oh, again, that's 1. Oh, yes, finally another yes. And then the last one says 3 cosine of 2x minus 1 and 4 sine of 3x minus 2. Now, normally we're used to the number being out front, so we can think of it as like 2 times x plus or minus something, and then 3 times x plus or minus something. I don't even care what that plus or minus something is. It doesn't matter. The horizontal shift doesn't matter. What matters is the period and the compression or stretch. So 2 and 3, those are different b's, but I can still check anyway. 2 pi divided by 2 is pi, and then 2 pi divided by 3, well, that's not pi, so we're going to say no. That's all that is. We do very, very little with 4/6. It's just not that important. I truly don't know what that alarm was for, but I'm here, so okay. I have no idea what I was saying, but sinusoid this is all we're doing for 4/6. Any questions? Okay, let's jump to 4/8. This is actually kind of a good practice from 4/2, which is going to be on your test tomorrow. So again, I'm sorry we're doing things out of order, but I did think if I had to move forward, this is a good one to move forward with because it's very similar to what you're going to be tested on. So we're just doing some word problems. Draw a picture, write an equation, solve. Round to the nearest hundredth, so 2 places after the decimal. So I will try and make sure that's written on your test. If you're in doubt, always ask. There's no problem in asking. I'm not too crazy about decimal points, but let's try and be consistent. Let's go 2 places. All right. So we're just going to draw some pictures. Find the angle of elevation of a bird in the top of a tree from a point on the ground 100 feet from the base of the tree. The bird is 18 feet above ground. Okay, so we're going to draw a picture. My triangle. Here's my tree and the bird's at the top of the tree. It says the bird is 18 feet above ground. So I'm going to label that vertical distance from the bird to the ground 18 feet. It says that from a point on the ground 100 feet from the base of the tree. So there's a point on the ground out here that's 100 feet from the bottom of the tree. And it says that what we're finding is the angle of elevation. Remember, angle of elevation is like looking upwards. So if I'm flat here and looking upwards, that's my angle of elevation. That's my P right here. Angle of depression is looking downwards. That would be up here. I never say never because in math, there's seldom a never. There's always an exception, but we almost never find this angle. Like we normally don't ever use this angle. It's not an important one. It's not angle of depression. It's not an elevation. It's really nothing. So we often do not use that. So don't think that automatically you're going to go put something in that if you're looking from the top. But this time we're looking for angle of elevation. So I'm just going to label that theta. Now, in case you don't have it tattooed in your brain already, let's write SOHCAHTOA at the top of our page. SOHCAHTOA. We're just using our three basic trig functions here, sine, cosine, tangent, and it just is based on the information given to us. So in this case, I have theta, or I guess I want to find theta. I'm going to say I have it even if I don't have it, because that's what I need to find. I need to find this angle. So I need to use this in my step. I also have my opposite. We know hypotenuse is across from the right angle, which I don't have and I don't want, but I do have my adjacent. So opposite, adjacent, and my angle, that means that we're using TOA, tangent. Now again, I'm not going to say always, because in a minute we won't use tangent, but we use tangent a lot in these word problems. So I would double check, make sure you carefully read your words. If you're using sine, if you're using sine and cosine too much, you're probably wrong. And if you use tangent and tangent and tangent and tangent, don't think that you're incorrect just because you're using the same thing over and over. So I'm going to write tangent of theta equals 18 over 100. Most of us do a good job getting this far. Now, when we were in 4.2, some of us had the questions like, kind of like, now what? Like, how do I solve this? And we're going to cover this more in 4.7, but I thought it was a little too confusing to do all of 4.7 today. We have to do the inverse of tangent to move it over. So the opposite of tangent is going to be tangent to the negative first. So to get it to go to the other side, we have to do inverse tangent or tan to the -1, or second tangent is physically what you're writing in the calculator. Second tan are the two buttons you're pressing. And then we're going to do 18 divided by 100. Okay. So let me pull my calculator back up. We actually needed a lot in this section. I really thought I could just drag it over. Make it a little smaller. We don't need it that big. So I'm going to do second tangent 18 divided by 100. Okay, enter. Ooh, it's saying my angle is 0.178 blah, blah, blah. We don't really ever do angles that are like already decimals. When this happens and you're like, huh, that's weird, I want you to go check your mode before you do anything else. Now, we just a minute ago put our calculator in radians so that we could graph it. I, though, want my angle in degrees. We do everything in degrees. We always talk about degrees. We're used to degrees. Radians are kind of this new weird thing. So I don't really want to do radians if I don't have to. So I'm going to jump over and put it in degrees and retype this in, and it should give me an answer that makes a little bit more sense. Ooh. Oh. Second tangent, 18 divided by 100. Okay, perfect. 10 is kind of a weird number, but it's not as weird as a decimal. So we could have an angle of elevation that's only 10 degrees. That's okay. So I'm going to say theta is equal to 10.2. 100th place would be 0. That's redundant. I'm not going to write 0 down. Okay. Questions, thoughts, comments on that first one? Angle of elevation, 10 degrees. All right, let's do another one. Find the distance from a worm on the ground to a bird in the top of the tree if the bird's angle of depression to the worm is 24 degrees and the tree is 19 feet tall. Okay, let's draw a picture. When in doubt, draw your picture. Oh God, okay. 19 feet tall. The bird is at the top of the tree. The worm is on the ground. And we know that the angle of depression from the bird to the worm is 24 degrees. So angle of depression would be up here. Now, if you remember back to geometry, we spent like a whole bunch of time talking about like if lines are parallel, then these kind of angles are congruent. We're cut by a transversal. These angles, the ones that I have marked, are opposite or alternate interior, so they're congruent. So that means that the angle at the worm is also 24. So you don't even have to draw that angle of elevation, or sorry, that angle of depression if you know this one at the W is also going to be 24. All right, and then it says find the distance from a worm to the bird. So the distance we actually want to find here is this one, from the worm to the bird. I want this like kind of diagonal distance, not a horizontal or a vertical one. I want kind of the slanted distance from the worm to the bird. So now we got to label our sides to figure out which trig function we're using. I've got my tangent, I've got my angle. My opposite is 19. My hypotenuse is X, which I want. And my adjacent, we don't have anything there. So I don't want anything with my adjacent. So I have angle, I have opposite, and I have hypotenuse, which means that we are doing sine. So I'm going to do sine of my angle, which is 24, equals O over H, 19 over X. All right, multiply by X on both sides. And we've done this before back in 4.2. If you forgot, go back and look at your notes. Divide by sine of 24 on both sides. And I'm going to put 19 divided by sine of 24. And I get 46.71. This is distance, so it's feet. Cool. Any questions? Okay.
Did you do that in radians or was it still in degrees?
I believe I'm still in degrees. Good question, Whitley. Okay. I need to step out for 1 second, so I want you to try the next one, and then we'll go over it in 1 second when I come back, okay? All right, my bad, guys. Passing period goes really quick, so I'm sorry for pausing us, but I hope you got to look at this one. So I'm just going to kind of speed race through it. It says how tall is a flagpole that casts a 23-foot shadow. If I could draw a triangle today, that'd be awesome. Okay. When the angle of elevation of the sun is 32 degrees. Don't get too bent out of shape about stuff. If it says angle of elevation, you're always looking at that bottom angle. We want to know how tall the flagpole is. The shadow casts from the flagpole is 23 feet. So I've got angle, I've got opposite. I don't have hypotenuse, but I do have adjacent. So that means I am doing tangent. Again, I don't like to say always. I don't like to say never in math because there's usually an exception, but we do a lot of tangents. So don't double guess yourself if you're doing a lot of tangents. Tan of 32 equals X over 23. And this is actually a super simple one because just multiply 23 on both sides and we're done. So I'm physically putting in 23 tan of 32 equals X in my calculator. And we did just check, I'm still in degrees. So I get 14.37. And this was again a distance, so I'm going to say feet. Make sure to label your answer, whether it's degrees or feet. All right, I know I went through that quickly, but are we okay with that? Awesome, okay. Next one, Kirsten places her surveyor telescope on top of a tripod 5 feet above ground. She measures an 8-degree elevation above the horizontal to the top of the tree that is 120 feet away. How tall is the tree? Okay. This one gets a little bit harder because we've got to add something in. So I've got my tree right here, and then I've got a tripod that is 5 feet above ground. We're measuring our angle from the top of the tripod, and it says from the horizontal. So that means we're going straight horizontal from the top of the tripod, and then the angle from there to the top of the tree is 8 degrees. So that means that I'm only measuring a part of the tree. I'm going to have to add 5 to that once I find the distance of the tree. So once I find this X, the height, I'm going to have to add 5 more feet to it because we cut 5 feet off based on our tripod. It says that we're 120 feet away from the tree and we want to know how tall it is. So I put X as my vertical distance and my distance away is horizontal. So that's 120. Anybody questions with my picture? Okay, I've got my theta, I've got my opposite at X, and I've got my adjacent at 120. That means I've got TOA, opposite over adjacent. Tangent of 8 equals X over 120. Multiply by 120 on both sides. So I'm physically putting 120 tangent of 8 into the calculator. I know 8's kind of a small degree, but it tells me it's 8 degrees. So I know that I'm still in degrees. We're still in the same mode. We want it to be like the same language as we're talking. So if I'm talking degrees, I want the calculator to also talk degrees to me. So when I put that in, I press enter, I get 16.86. But that's just from the top of the tree to where the tripod was. So I'm gonna have to add 5 to that to actually find the entire height of the tree. So 16 plus 5 is gonna be 21.86 feet. Anybody questions on that? Going once, going twice. Okay, we're actually going to skip number 3 to next time we have class. I tried to do the problems that I thought were most similar to 4.2 today, and then we'll do the rest later. We're also going to leave number 4 to the next day in class too. So we'll do 5, 6, and 7, and then I think that's it for today. Everybody good on that first page that we've done so far? All right. Again, I hope you find this at least a little bit of a useful review or nothing that's too hard yet. So number 5, we had a little bit of something complicated because it tells me the degree with a degree minutes seconds. So everything else in this problem is fine and normal. The one step that I added that makes it a little bit harder is now we have to make this minutes seconds into just a decimal of the degree. So even before I draw my picture, I'm going to make this into a degree decimal. So I have 34 degrees, 13 minutes, and 12 seconds. And this is actually on our test, so this is a great review. So I'm going from 13 minutes to degrees, so I'm going to multiply that by 1 degree over 60 minutes. So 13 divided by 60. If you knew you were just divided by 60, you don't have to write it like me. I just don't always remember if I'm multiplying or dividing. So I like to do the units and then know that the units go opposite each other. So do what makes the most sense in your brain. This makes the most sense in mine. So it's going to be 0.216667. Don't round too crazy close right now. You're going to see in a second that it'll work out nicely. And even if it doesn't work out nicely, try and hold as many places after the decimal as long as you can. And then at the very end, then we'll cut it short. But this is actually going to work out nicely. Now I've got 12 seconds and I need to make seconds into degrees. So 1 degree is the same thing as 3,600 seconds. Which again, we should just know because we're getting tested on that tomorrow. So I'm going to cross out my seconds and do 12 divided by 3,600. And I get 0.0033333333. So let me add those two together. Again, carry it through as much as possible. So I still have my answer hanging out in my calculator, and I'm just adding the first one, 0.21666667. Ooh, and I told you, it did work out nicely. I get 22 or 0.22. It doesn't always work out that nicely, but today it did, so we're going to use it. So this is the same thing as 34.22 degrees. Now, if all I asked you was to put that in degrees, from degrees, minutes, seconds to decimals, we would be done. However, the question wasn't, what is this in terms of a decimal degree? The question is, how tall is the monument? Well, truly, I haven't even read the rest of the question. I just made this into a number that makes sense for me to put on a picture. Now I'm going to read the rest of the question so I can draw a picture and actually find how tall this monument is. So the question says, from a point 100 feet from its base, the angle of elevation of the top of the Arch of Septimus Severus. Sounds like a Harry Potter name. That's weird. In Rome, Italy, is this degree we just found, 34.22. And it says, how tall is this monument? Okay. Everything we're doing is a right angle, right triangle. Right. 100 feet from its base. So here's the point, and we are 100 feet from the base of the monument, and we want to know how tall the monument is. And it says the angle of elevation. So that's the angle down here at P. That's my 34.22. And then we solve from there. Drew my picture. Let's label it to figure out which trig function I'm using. There's my theta. There's my opposite. There's my adjacent. Oh, nice. I'm going to do tangent of 34.22 equals x over 100. I don't know why that's so messy. And this one's actually easy. Just multiply by 100 on both sides, plug into our calculator, and then we're done. The hardest part about this was making sure that we could go from degrees, minutes, seconds into decimals. So I'm just typing in my calculator now, 100 tangent of 34.22, enter 68.01. Oop, put feet. That's how tall my monument is. Again, the only step up the ladder we took, the rung up the ladder we went up, was just that we had to do a little bit of work before we could draw our picture. Any questions so far? All right, let's look at the next one. This one's actually an easier one than that one, so we'll just kind of skate through this one. The angle of depression from the top of the Smoketown Lighthouse is 120 feet above the surface of the water. To a buoy is 10 degrees. How far is the buoy from the lighthouse? Now we could get all bent out of shape about like the tree, kind of like the tree problem we just did, where we're like, well, are we X amount of feet above the water? It doesn't tell us, so we're not going to make it harder than it has to be. We're going to assume this is like a low buoy that's just right on the surface of the water, not one that's like 2, 3, 4 feet above ground. So just let it be low, no extra value. So the lighthouse is 120 feet above the surface of the water. So that vertical distance is 120. The angle of depression is coming from the top, which is 10, which we know can also be written down here as 10. Ooh, I don't know why that's so messy. And it says, how far is the buoy from the lighthouse? We're just going to use X. I've got my theta of my angle. I've got my opposite of 120. I don't have hypotenuse, but I do want adjacent. So I need to do opposite and adjacent, which means I'm doing tangent. Ooh, sorry. Tangent of 10 equals 120 over X. And this is the hardest part of the problem, which we've done even harder than this, but just make sure you multiply by X from both sides and then divide by tangent. So we divide by tan 10 from both sides. So in the calculator, I'm physically putting 120 divided by tangent of 10. And I have not moved from degrees. So I'm trusting myself, it's in degrees. So 680.55 feet. That's how far away the buoy is from the top of, or from the base of the lighthouse. The biggest piece of advice is, like, we might be skating through this and you might say, I know exactly what Miss White is doing. I know why she's labeling stuff. I know which function she's using. I am all good. The biggest mistake is making sure that you can plug this in and get the same thing. So even if you're like easy peasy and you're just letting me plug it into the calculator, I would go back and practice to make sure you also get the same answer, because it could be something as simple as your mode being wrong, and that would be a silly way to lose a bunch of points on the test. Or you might not remember which trig function it is, or maybe you wrote tan on your paper, but you're pressing sign in the calculator. So do yourself a favor, go back over the motions, make sure that you can physically plug this in the calculator and get the same answer. Okay. We're gonna do one more today, and this is gonna be the hardest one we've done today, only because it's not just gonna be one triangle, and you're gonna see in 1 second. So everything else is pretty easy and stuff that actually could be on this most recent test, or this test that you're taking tomorrow. This one is a little bit tougher because I'm dealing with two shapes, not just one. So let's draw what's happening so you can understand why I know this is going to be two different triangles. From the top of a 100-foot tall building, a man observes a car moving towards the building. Okay, so let's stop there. Let's start drawing. So we've got this shape. We've got a 100-foot tall building. We've got a man at the top, and he sees a car moving towards the building. So the car is moving towards the building. If the angle of depression of the car changes from 22 to 46 during the period of observation, how far does the car travel? So essentially, as he's sitting there watching it, the car goes from here and it moves closer to the building, and now it's here. Okay. The angle of depression when he first starts observing the car is 22. So that means that I can go do this far angle is 22 degrees away. I feel safe about doing that. That's fine. That's stuff we've done before. Now, then it gives me another angle measure, which we've never done before. We've never had two angle measures. That doesn't refer to anything else in the triangle. I have to draw a new triangle. So now I've got this triangle, this darker triangle that goes from my new C. It still is a 100-foot tall building, but now my angle of depression isn't 22, it's 46. So now the big angle, this new big angle that's now down here is 46 degrees. I want to know this distance right here. Let's separate these two triangles and then kind of see how we can solve. So I've got a longer triangle, 100, 22, And then we've got to do something with the bottom, but I'm not going to label that yet. Questions on what I've labeled so far? Now I'm doing a skinnier right triangle because this one is still 100 feet tall of a building, but now my angle of elevation is 46, not 22. I'm going to label this distance X. So where the car ends up to the base of the building is going to be X. But that's not what I want. I want to know the distance from where the car started to where the car ended. To merge these two together, if this distance from where the car ends to the base of the building is X, then I've got an X right here on my light blue graph. Let's use a different variable to represent what we want to find. We want to find this distance right here. I'm going to call it D. So the first triangle I have is not just X or D as the bottom, it's going to be X plus D, because I've got one distance, which is how far the car traveled, and then the other distance is how far the car ends up to the base of the building. Now this is actually going to be pretty simple. We just have to solve one triangle before we do the other one. Let's do the one that only has one variable, right? I can't solve it if there's two variables in it. But if I take this like darker triangle right here and solve for X, I'm going to get tangent of 46 equals 100 over X. Again, multiply X by both sides, divide by tan 46 on both sides. So in the calculator, I'm physically putting in 100 divided by tan of 46, but that's going to tell me how far the car ends up from the base of the building. .57 feet. Now again, not my answer. My answer needs to be from where the car started to where the car ends. That's going to be my D. But X is helpful because now instead of having two variables in the first triangle, now I just have one variable because I can replace X with 96.57. So I'm going to write that trig equation. I've got tangent again. I still have my opposite. I still have my adjacent. So I'm going to do tan of 22 equals 100. And this time it's not just over D, it's going to be D plus X, which we just found was 96.57. We're going to solve this in the exact same way. So we got to multiply by the denominator, but don't get too crazy. Don't distribute it. I'm going to leave it as just D plus 96.57 times tangent of 22. I know we're itching to distribute, but please do not. It's going to be easier if we don't. And since these two things are being multiplied together, we can divide by tan 22 on both sides. So I can get D plus 96.57 equals 100 over tan of 22. Let's stop here and plug that right side into the calculator. 100 divided by tan of 22. Now I've got like an easy algebra 1 equation. D plus 96.57 equals 247.51 minus the 96.57 from both sides. And I get 150.94 feet. I'm going to zoom out and I'm going to get rid of the calculator because I don't need it anymore, just so you can see this whole problem. So what we had to do was draw our situation and recognize what we were looking for. How far does the car travel? That's not how close to the base of the building it is. That's not how far is the car from the man. It's how far does the car travel? So we had two variables and we had to find the first one. We had to find X before we could find D. Now the other two problems we'll look at next class. I think we're not done for a few more minutes, but I am officially done with the lesson today. So you are welcome to stay on and ask me any questions, or you're welcome to join the Zoom tonight at 7:30, or you're welcome to come in tomorrow before school, or you're welcome to not do any of those things and just be ready to test. So if you need me, I'm here. If not, have a good rest of your day. I'll see you guys later.
Thank you.
What lessons
you.
are